Um, okay, thanks for the introduction. I'm going to present our paper, Lossless Space Expansion for gradient domain rendering. And this was collaborated with my supervisor, Toshia Hajiska. Yeah, so let's get started. So just some background. So in rendering, like specifically physical-based rendering, that we usually we are trying to solve the color for the image for each pixel. So normally what we do is that we compute like the integral for each pixel or the path space or possible path space, and we do this independently for each pixel. So for example, like this green and orange pixel, that they have different integration domain and slightly different integration domain, and we are just integrating over them to get the final pixel color. Yeah, so traditionally, what we do is we just apply Monte Carlo method that we compute the sum over all the samples that draws from the probability distribution that we choose for each pixel pi, for example, and then we have an unbiased estimation for that particular pixel. So just some background for gradient domain rendering. So so let's consider this scene. So we have two simple objects and a camera that this camera is actually like a 3D camera. Yeah, so we have a light source, and so if we render like this blue pixel, for example, then we trace a ray, and then we hit the first object, and then we continue trace the ray until we hit the light source. So let's consider that we have another pixel, for example, like this red one, that the first ray we still have to deterministically trace it. But after we trace the first ray and we hit the surface, and we notice that we already traced a ray on the neighboring pixel, on the first pixel, like in color blue. And so what we want to do is that we consider we want to trace a correlated path that utilize the information from the first path that we traced. So that we hit the first surface, and then we just directly connect the path with the second hit point. So and then we have a correlated path generated by this reconnection shift that which already discussed with the previous talks. But yeah, so fortunately I don't have to explain it over again. But in this way, we can see these two paths, they have similar contribution because they generate from similar paths that just shift by a little bit. So and these two paths, they have a very low variance difference estimate that we obtained. So with this low variance difference estimates, so originally we only have the Monte Carlo estimates for each pixel, and then now we have a low variance difference estimates that is computed with this bidirectional how do I say this Monte Carlo difference estimates computed with both direction shift mapping. So it looks a little bit scary, but it's just so this Tij is just a shift mapping function that we use to shift paths from I to J, and this is just simply the Jacobian that used to make the contribution correct. And this is the MIS weights that make sure that you have paths that generate from both domain that sum to they sum to one, so that we have an unbiased estimation for the difference. So so because this difference estimation is lower, is particularly lower variance than our primary domain estimates. So we can use a Poisson reconstruction process that was usually has been applying image processing tasks. So we just solved this minimization problem. So let me just elaborate a little bit. So the first part of the loss target is just the difference term that we want to minimize the difference between the estimated difference and the actual difference that we compute. And also, like we have a second term, that's the regularization term that we just want to minimize the difference with the of our estimated image color with the multicolor estimate that we have. Yeah, so that's basically some background about gradient rendering. So yeah, so there are a lot of literatures, almost like all like subfield of like ray tracing, like for example, MLT, like simple path tracing and bidirectional path tracing, vertex convolution merging, etc. Like they all have like this kind of like gradient domain rendering counterparts that has a paper, and there's a survey like for the last paper, like there's a survey that's just discussed like all those like shape mapping techniques and some discussion about like the related works. So I strongly suggest like interested readers can like go through the last article that so you can get more details about how things work in implementation for gradient domain rendering. Yeah, so but like we have discovered a problem that have like limits the use for gradient domain rendering. So still consider this slightly different thing that like we have a object that's textured with high frequency that has a high frequency texture. So usually like the normal and the albedos are changing, are changing quite frequently over like the pixel space. So still like we can use like gradient domain rendering to like first we generate a ray and then we still generate a different ray that's using the same technique as like gradient domain rendering. But in this case, like you can see that the path contribution now is very different from each other. This is because like when you hit the surface and then because like the first hit and the first pixel and the second pixel they hit like slightly different position, and because like they have like very high frequency albedo and normal, so the BSDF value changes quite significantly between these two pixels. So this means that you will get like a higher high variance difference, unlike like previously what we talked about some like smooth surface. So, but if you look closely, that if we let's assume that we are just doing like reconnection shift, then we still have like this similar incoming radiance that's like this second line segment, which is still good, but this time like the difference comes from the difference BSDF evaluation. So and just before talking about our work, like I'm gonna just go over some orthogonal work in gradient rendering. So there's like one work that's using some regularization technique that focus on regularize like improving the regularization term for gradient domain rendering. So basically they have a G buffer or like some features that they assume that the image patches are reconstructed with those the basis that's being used to the basis that computed from those G buffers. So you have like you have a better regularization over the reconstruction step. And there's like more recent work that's using like convolutional neural network to perform this reconstruction step in gradient domain rendering. So they also use the G buffer and also the difference estimates to have a better reconstruction. Yeah. So, but these two techniques, they are they're biased, and from the nature of their algorithm, like they cannot be made unbiased, and if they don't combine like weight their results with the like regular gradient domain learning or regular path tracing, they cannot get a consistent result. Yeah, and one thing is that they still use like noisy difference estimates. Yeah, so our work focuses on extracting those like low variance difference information, unlike traditional gradient domain learning when you hit like the same hit the first surface that you have like high frequency albedo and normal. So our work focuses on extracting more low variance estimates from using gradient domain learning. So yeah, so we can take a closer look at the rendering equation. So consider a pinhole camera that we are just like shoot a ray from the pixel and then we hit the first surface. So the left part is just the pixel intensity that we want to extract. And so for this first blue box that we have, is just the incoming radiance of the first hit first hit point. And then the second part is the cosine weighted BSDF term that we have. So we denote HI and GI for simplicity. So we're just simplifying this problem into a product integral of HI and GI. Yeah, and as we said, like the first part is smooth, like over like across pixels, and the second part varies significantly between pixels. So consider this like a simplified constructed problem. So we want to solve like the pixel color for this checkerboard, and so for the lighter block, we're just solving this like red function that's a step function times the h. That's just a linear function. It can be any function, but we just choose a linear function for simplicity. And the green part like have a different signal than the red function. So basically, like if we simply apply gradient domain rendering, then what we get is like this really strange image that you can see like some artifacts across the edges of these two colors. This is because like when you're crossing the edges, like you can see if you extract the red part and the red function and the green function, then you'll get like still you don't get a constant function. You'll get like something that has non-zero variance. Even though like in the same color region that you will get when you are crossing pixel, that you will get the same zero variance estimate, but when you are crossing the pixels, then crossing different colors, then you will get like a non-zero variance. So that's why you get this non-perfect image. Yeah, so there's a proposed solution that we have. Is that like we solve these two integrals like independently to each other. So if we assume like the whole image is all the pixel in the whole image is solving the same integral, then we apply gradient domain rendering, and we can get an unbiased result. Sorry, like a very clean result. And then like same for the bottom target, that we will get like a different result, but also like almost noise free. And then after that we combine these two results based on what color is there, what color the pixel is. So basically like we can combine the result afterwards when we do GPT on for each of them. So you can see like now the result looks much cleaner and it's almost noise free. So just for reference that we compare the difference, so you can see almost like our proposed solution is much cleaner, and the middle one is just like naive gradient domain rendering, that you can see there's there's like high arrow in between the like when you're crossing the regions. Yeah. So more generalizing our method to more to rendering that I just gonna provide the overview of our method. So basically, like originally we want to solve like this integral for our rendering target. And then like if we apply naive gradient rendering, then we get like this high variance difference. So let's now like we consider expanding like the GI term into a like with a basis expansion. So let's assume that I will explain later, but let's assume that now the basis expansion will completely recover the GI without any residual. Okay, so and now like we can like do some math and just change our original integration target to a weighted sum of different integration target. So now if we solve each integral separately, like each integral, you can see now they have like a much lower variance for each integration target, and hopefully like we'll get a better result. Yeah. And it's worth mentioning there's a previous work in denoising. So basically like how they do things is that they extract the albedo from so before they apply denoising algorithm, they extract the albedos from the BSDF, and then they multiply the albedo after they apply denoising algorithm. They apply any kind of like denoising algorithm. So you can see from their result there, if they apply denoising algorithm naively, they will get something like a blurry image. But if they apply they extract the albedo out and then they multiply it afterwards, they get a much sharper image. So this is actually equivalent to our method with a single basis. But in their case that they cannot handle normal variation. Consider you have like the same albedo area, but you just like where you have a different like a high variance normal map. Yeah, so our method can handle like both albedo and normal change within the same framework. Yeah, so let's review. So I'm gonna talk about how we do this kind of like lossless basis expansion that we can completely recover the original target function. So basis expansion, we usually have this like GI approximately equal to some weighted sum of bases. But we want to have like full recovery of this cosine weighted BSDF term. So what we can do is that like because like we just want low variance difference estimate. So what we can do is that we can have like slightly different bases across different pixels. But we don't have to be exactly the same. For example, the BSDF doesn't have to be exactly the same to get a noise-free image. When you apply denoising or gradient rendering, it can be slightly different. So what we want is that we can have pixel based basis for our basis expansion. So we call it lossless basis expansion. But the question is how we decide what this lossless basis should be in our case. It turns out quite simple. So we consider that we just have a residual term that we will get from our basis expansion, and then we do some math tricks, and then we have like we just take the we just plug the residual in, and we can have like this weighted weights that sum to 1 for the residuals. And then if we extract the alpha I out, then we will get this second parts that we can formulate as our lossless spaces. Yeah, so that's how we get our target. Yeah, so this is actually just one example that how we can get our basis. There are other choices, but in our experiment we didn't find those choices make any improvement. So we just like empirically choose this one as our lossless basis. So and now it comes to reconstruction. So let's define our basis image as the integral of incoming radiance times our lossless basis. And then our original image can be computed just by weighted sum of like this basis image that we obtain. So if we recall our reconstruction target for naive gradient rendering, that we get that we can just simply apply gradient rendering on each of the basis image, but yeah, we can still get a valid solution for all the basis image, and we still get unbiased results. But actually, like we find that we can do better. Yeah, so we have like this looks a bit. We have this target that looks a little bit messy, but if we break it apart, like so, this part is just simply the difference term that's similar to regular gradient rendering, except for that we applied it on each of the bases. And the second part is the regularization term. So basically, like what's different between our previous target is that now like we just need to regularize towards the Monte Carlo estimate for the original image instead of we regularize towards each independent basis image. So the benefit of that is that we have for example, if some bases they have like a small coefficients, then we essentially don't care about that basis in that particular pixel. So and then our final estimation is simply just the weighted sum of those basis estimates. Yeah, so let's look at some results. So we apply some high variation texture in both the, like in this case, the kitchen sink and the bedroom sink. So the kitchen sink, we have some albedo and roughness changes. Yeah, so you can see like the noise actually like reduce a lot. If you specifically look at this, like when it's crossing the boundaries, that variance actually it has like quite high variance in the in gradient rendering, but in our case that it's much cleaner. Yeah, and also in the bedroom scene, like the albedo stays the same, and we have like a high variance normal map apply on it. Yeah, so you can also see that our method, like with different basis function, also reduce the noise quite a lot. Yeah, so this just some further examples. So you can see like it's actually interesting that in L2 reconstruction, in some cases that we actually reduce the like we actually sometimes we can see the dipole artifact from gradient domain rendering are removed with our method with our spherical harmonic basis. Yeah, and so also for this staircase that the albedo changes a lot. So yeah, you can see our method works significantly better than the baseline. Yeah, so these are some failure cases. I put the quotation mark because they are actually not that bad. Like we still numerically get better results, but because I think the texture doesn't vary that much. like they are quite spaced with each spaced separately. So it seems like yeah, visually like qualitatively it doesn't seem that much of a difference, but numerically we still see benefits. Yeah, so these are just some numerical results that we have. Yeah, so you can see that our method numerically performs better than traditional gradient domain both in L1 and L2 reconstruction. So these are just some results that we test our method with a different number of bases. So so for example, with single bases that you can see in this particular example that you can see the albedo changes is cancelled, but you can still see the noise in the normal variation part. Yeah, so this is another fellow case that actually like we can handle albedo and normal variation very successfully, but with only roughness change that we kind of our result is comparable to the baseline, but it's just because our method needs more time to run. So that's yeah. So the limitation of our method is that we doesn't support our method doesn't support real lens camera or pixel filters. So this is like one of the major limitations of our method. So, but this is actually like similar to other methods like for example the convolution, the deep learning method or the regularization method that using the G buffers. But like anti-aliasing can be achieved by rendering a higher resolution image followed by downsampling. So we didn't see. So we still think like that's a common approach. Yeah. So and our method because like we have to do basic expansion for the first hit BSEF. So our method doesn't support like position-free Monte Carlo, for example. Yeah. So there's some future work. So like we can pre-process the basic expansion for each kind of materials, and so we can mitigate that. We can eliminate the pre-computation cost for the basis expansion, and also like our method can potentially be applied to Riester, but maybe we need a different formulation because Riester automatically handle albedo variation, and we can also apply our method in denoising. So in conclusion, our method extend the albedo factorization trick to more general type of per pixel variation. And we also propose this lossless expansion, lossless basis expansion. And also we use a more robust reconstruction target, which focus on parts that matters. Yeah, thank you.